Without further ado, welcome everybody to the first webinar of the year. This is the AIAA Space Resources webinar series. I'm Jared Longfox, your host, well, one of the hosts. Today, we're lucky enough to have Dr. Vlada Stamenkovic from Blue Origin, the Senior Director of the Space Resources Program, here to talk to us today about space resources for the benefit of Earth. I won't take too much of his time, but I will note, if you guys have any questions, please punch them in the Q&A, and we'll get to them at the end in the order that they were received. So thank you, Vlada, for lending your time here, and I look forward to the talk.
Jared, thank you very much. Can you hear me?
Yes, we can.
Wonderful. So I'm staring at my screen, but I'm imagining there's a lot of people all over the world. So hello, good morning, good afternoon, whatever, wherever you are. Hope you have a good day. I'm going to be talking about our efforts at Blue Origin on space resources and what we're really doing as much as we can share right now, and how these technologies are also beneficial and helping to benefit the Earth. And before I really dive deeper into this, I'm talking, it's my privilege here to talk and to represent, but I really want to highlight that this is, of course, not just me doing this. I have behind me a wonderful and amazing team inside the Space Resources Program, but also in space systems development and the Greater Blue Origin. And this has been a indeed amazing team effort, which would have never been possible without having people from all kinds of capabilities across diverse disciplines and backgrounds doing this together. And this is right now a most recent picture of a big chunk of our team here in the LA Hills. So we actually go in Los Angeles. I'll talk more about that. After celebrating 2023, the successes, went horseback riding. So that's what you do in LA, of course, when you celebrate something. And I just want to really say, first, most importantly, my gratitude to my team, to all those amazing individuals who have made this a success. So let's get started. This is right now in our current co-shared space with Honeybee Robotics, who are really wonderful to allow us to enter their premises and do our work here in Altadena at Honeybee Robotics in their facilities. What you see over here is something I'm going to walk you through in the next 45 minutes or so, which is showing really what we're doing in our lab currently, or showing specifically one thing. It's illustrating right now how we're utilizing regolith simulants and transforming them into solar cells and making sure to infuse this into a system that will be able to generate solar power on the moon. But that's happening in the lab. And that's really what hands are doing today. But I want to start with our motivation. And, I am, as many of you, I think, big trekkers, big Star Trek fans. For me, that's not just something I like to watch, but something that I like to try to help create a society where people are explorers, diverse kinds of people, and having time to really explore the universe. And there's one gadget in Star Trek that ultimately I think we as humanity have to generate. And I hope I'll be able to illustrate that the work we do today is on path to that. Very, very early, but on path to that. And what we see over here is for those experts in the field, you might notice that Picard is here actually not really on his own body. That would be Janeway, because you see Chakotay in the background. So that's a little subtle hint here. But we see a replicator, which is a system that ultimately, has some energy and transforms energy into matter and makes tea, Earl Grey, hot, or anything else you want. And it's the ultimate power that a society, I think, should have, is to transform energy into all forms of matter. And theoretically, we know that's possible. Practically, we might not be there yet. But the thing that I'd like to show now is that what we're doing in space systems development in Blue Origin, specifically in the Space Resources Program, is on path to enable a system like this down in the future. But to do that, we're starting with the ability to actually look at space resources and look at what's just around us and give meaning to things that maybe are not as meaningful initially, and make meaningful products. And that is something that is core, fundamentally important to Blue Origin's vision, which is to have millions of people living and working in space for the benefit of Earth. And when we look at the Earth, we do recognize that from a planetary science perspective, it's maybe hard to say it's the best planet in the solar system because, people who love Venus science might disagree, Martians as well. But what we all humans can agree, I think, is that it's the only place to date that we know that we can live there, and we can live as we are. We have beautiful things around us. We have food, we have fresh air, we have everything we need to flourish. And no, we don't know of any other object so far today that enables the same thing. So we got to really be careful and take care and be good shepherds of our own world. And we know that the Earth is finite. I mean, that's something that we've, I think, known for many decades now, but especially in the 21st century, we actually do really understand and feel it in our own skin. We see how specific materials, water, metals, are actually limited in their availability. We see as well that certain elements like carbon dioxide, for example, can have a profound effect on our planet. We see that the fact that the Earth is finite is actually limiting us in order to live a good life and to flourish and expand. We know, however, that space resources in many ways are abundant from our current perspective. The solar system has a lot to offer, much more than what we find in the shallow crust of the Earth, which we usually utilize in order to get things done, from our cell phones, computers, to our houses. Now, Blue Origin's mission is embedded in that realization by realizing the next to radical launch cost reduction and inspiring next generation. We really have to focus on learning how to develop technologies to utilize space resources. And utilizing space resources has two key elements. One is to learn where important resources are, for example, like water on the moon, or potentially specific metals in near-Earth objects or asteroids, and to learn how to utilize them for the benefit of building a cislunar economy and a planetary society, but also benefiting actually the Earth directly. But the second aspect is to learn to live with little, to learn to utilize anything that we find around us. And we start with regolith, for example, or rocks. And with those things that are not very valuable, make valuable things. And that's the connection I tried to make to our replicator, where initially we start with energy and we transform this into anything we want. Well, we're not there yet, but we're learning to utilize things that many people call dirt, and don't really associate much value to it. And we're trying to make valuable things with that. And that's important for living on the moon and in a solar system. But it's also important, as I will show in my talk, on the Earth today. So at the Space Resources Program, we are responsible for developing those technologies that enable the second mission, the utilization of space resources. We're responsible for developing the roadmap, the models, the concepts, and the technologies that will allow us to utilize resources on the moon and beyond to enable humans and robotic explorers stay there, not just to visit, but to actually stay there and live there and explore. But we're also chartered to utilize these technologies to infuse on this planet to help solve issues that exist on this planet, and I'll show more later, and to really benefit the Earth, not just in the far future, but today, and solve problems that we face, that we need to solve ASAP. So the Space Resources Program is headquartered in Los Angeles. We've chosen this place mainly because it gives us the opportunity to really unite a lot of the different disciplines that are needed to solve these problems. We're very close to dear partners and allies at JPL, Honeywell Robotics, but we have also the chemical industry, the oil and gas industry here, and not to speak last of it, but also Hollywood, which helps us get to our dreams faster. So right now, we've got a team of about 25 people. And we are going to be about 40 people in February and should be already 60 people by June of this year. So please look out. There's a lot of job recs out there, and many more will drop again in February. We are very much looking to grow our team, and our team is fascinating because it unites all kinds of various capabilities. And that's what you need to answer these questions. We've got planetary scientists, geologists, geochemists, then chemical engineers, material scientists, semiconductor specialists, all kinds of engineers from mechanical, electrical systems. It really needs all these different disciplines that speak very different languages. And those different languages have to learn to understand each other. And then we can actually start understanding how to connect and solve the problems that they're dealing with. Because when you think about utilizing resources and making technological devices with this, you gotta address everything from bare, private, objects, ore bodies, rocks, sands, all the way to a very, technological high-tech system. And so right now, our focus at the Space Resources Program is really to focus on using space resources to create solar power systems. And I'm going to talk a lot about that, propellants, and also you'll see other infrastructure. Okay. And one thing that I'd like to highlight is as well, at Blue Origin, we are starting with the moon. The solar system, of course, is pretty big. And I'm trying to show this here where our roadmap is ultimately starting on the Earth, transitioning across the moon, utilizing the moon. On the path, of course, we're going to have near-Earth objects and asteroids. And down the line, we're trying to get millions of people living and working in space. I stole that as well from Star Trek. Credits are right there, so all good. But the journey after that will continue into who knows where. But in that space, we are starting with the moon as our springboard, as our stepping stone to learn how to develop those technologies, to build up cislunar infrastructure, to establish lunar permanence. But we are not a destination-focused technology. We're developing technologies that are independent of the destination. Now we'll work on the moon, work on near-Earth objects in the asteroid belt, and on Mars. And so it's really important to understand that as the Space Resources Program, we are not really focused on just one location. We're connecting the dots between many locations and giving them much more meaning, from ultimately working on the moon to the asteroid belt and utilizing sun in the Earth's orbit for the benefit of the Earth. But again, everyone has to start somewhere, and we're starting to put our feet, metaphorically speaking, and hopefully literally speaking soon, on the moon. Now, when we look at the moon, and generally everywhere in the solar system, I always joke around, there's two things one has to know how to utilize, and then you own the whole universe. And that's the dry and the icy stuff. Dry stuff, rocks, regolith in a crushed form. It's abundant everywhere. It's pretty much similar on, there's of course differences, but the main constituents are pretty much the same everywhere. And then there's, of course, also ices, water ices, methane, anything else. On the moon, we have an understanding that there's definitely hydrogen, specifically in the polar regions, but we don't yet fully understand in which form, in which abundance, whether that resource is really reserved or not. And that's a question we still need to address. And I'll talk more about the icy part, but because we know that regolith is there on the moon and in the rest of the solar system, we've decided to kickstart our space resources journey on the moon by focusing first on regolith. So most of you know that, but regolith is generally rocks that have been crushed over hundreds of millions to even sometimes billions of years. And it's pretty nasty stuff. It's pretty great stuff, but also nasty. It's, if you imagine compositionally, it will be like desiccated rocks mainly on the Earth. There's different regions on the moon when you look up there in the Marian highlands, more iron-rich versus more calcium aluminum-rich rocks. The target zones where we're heading to, the lunar South Pole, we expect more, because we're more in highlands, calcium and aluminum-rich igneous rocks, less rich in iron. But generally, compositionally, we know it contains, some elements of a metal or metalloid with oxygen. Those metals symbolized here with an X could be iron, silicon, aluminum, titanium, etc. But the bulk weight is oxygen. And oxygen, of course, is really exciting for us, but so are iron, silicon, aluminum, and titanium, and other of these metals and metalloids. Now, knowing that regolith is there, that it has oxygen and metals and metalloids in there that we could utilize, we're going to start our journey on the moon with our current system, our Blue Moon lander. This is an illustration going to be for Mark II. But we also have, and that's the one we're using and working with NASA to bring humans and Americans back to the moon. But we also have Mark I, which is a cargo version, which is dedicated to start launching soon. And our intent is to utilize this transportation capability of Blue Moon, Mark I, Mark II, to get to the moon and to start utilizing the regolith around us. And our ultimate goal is, or in this decade, to be able to use robotic devices that are capable of harvesting that regolith and making solar panels. And the reason why this is so important and why we think this is the first step that we need to do is because power is the primary thing that everyone needs. We can debate for hours, for weeks, what we want to do on the moon, and because everybody's going to want different things. But what we can definitely agree on is that everybody will need power. And a very simple, elegant way of harnessing power is to look at the sun and harness solar light and ultimately make power with that. Now, if we want to do anything meaningful on the moon, meaningful in the sense it's not just to go there and try it once or a little demo. We got to talk about megawatts of power or even larger. And I'll remind everybody, a dishwasher generally is about 1 to 2 kilowatts. So that's not too many dishwashers. And if you really want to do anything of an industrial commercial scale or even with human permanence, we got to get to the megawatts. And if we were to bring those solar panels from the Earth, it would be very, very expensive. Too expensive for, I think, anybody to really invest. But what we've designed is ultimately, we're building now a core technology. It's going to enable us to build and bring smaller systems, scalable systems to the moon that can, with regolith and driven only by solar power, generate more solar power. Theoretically, such a configuration has potential for exponential power growth if you tap into the power you already generated. So this is really an enabler to kickstart the lunar economy and the cislunar economy and open up the gate to the asteroids and near-Earth objects. What's also exciting, of course, as a byproduct, this technology maximizes to get oxygen out of regolith because it taps into the oxygen, not just stored in the iron, but in the silicon, aluminum, in other elements. So it really liberates most of the oxygen and is allowing us to really design commercially viable systems. And that's one thing that's very important to us, the Blue. And something that I had to learn the last 4 years being at Blue. We're not thinking about, hey, let's do a little demonstration. Of course, it's very, very important. And then we'll see how we get to a commercial system. We're taking this the other way around. We're saying, what does the commercial system need to look like? A commercial system that's generating megawatts of power, utilizing only a few, kilowatts or tens of kilowatts of initial seed power, and produce metric tons of oxygen. What does the system need to look like? And then we're doing a de-risking down and defining the technology we need to develop and doing the testing, the minimal testing we need on the Earth and potentially also on the moon in order to show, hey, we've got enough confidence that we can now build our full commercial system. And so Blue Alchemist is the core technology that we are using for enabling this specific system. And what I'm showing right now here is pretty much the diagram what Blue Alchemist is doing. It's driven by small amounts of external power. It's very efficiently melting regolith, storing whatever needs to be stored. And then we are going to a next process using molten regolith electrolysis at temperatures between 1600 and 2000 degrees Celsius to separate iron to separate silicon and aluminum from oxygen. And we're capturing the oxygen and purifying it to use for propellants or for human consumption. And then we're specifically focusing on silicon to purify it so to be able to get enough purity that we can make solar cells with this. What's really important about our system is we very much understand that we have to utilize as much as we can of our byproducts so we have little waste. And what we do is we use part of this, of the extraction byproducts to make backings for our solar panels and solar cells here. So that's the substrate production. We also making cover glass that helps us enhance the lifetime of these solar cells and ultimately solar panels and shift it from lives of weeks to years. And we're also utilizing aluminum to make wire. But the aluminum we make, we're also looking into other options to keep it just as powder and to utilize it for other things, for construction, for repairs, etc. But what I'm showing here in the 3 videos are just these 3 processes, step by step. Looking at melting molten regolith electrolysis, the black bubbles you see is actually oxygen being released, and ultimately making solar cells. What's really amazing is we've started this now in August of last year to work on a tipping point together with NASA and our partners. In the next 3 years, we will mature this technology and actually make a full terrestrial demonstration. That's going to happen in the next 2.5 years. Half a year's already over. It's going fast. And so this is really exciting because we can leverage the experience that NASA has and combine it with the startup approach that we have in our program, in our team, to actually, really be very hardware rich. So what we do is we're operating in scrums. For those who are not familiar with that, we get an amazing team that's, we call them our Blue Origin SEALs. We are integrating everything in all as it's developed, and we're testing and failing and repeating again. This allows us to not overthink and to really go straight to testing hardware and integrating it immediately as it's being added. So we're growing our system continuously and therefore understanding the feedback loops that are there between all the subsystems much quicker than if we would separate the subsystem individually and then integrate at the end. So we're trying to avoid that step by continuous integration of our subsystems so that within the next 2.5 years, we're going to have a full TRL-6 system ready and demonstrated to be applicable and implementable on the moon. Okay, let me go here back. Whew. So let me first do something really important. I'm going to talk later a bit more about water, but I'm going to have a little sip here. There we go. And this, what I'm showing here is actually a Blue Alchemist. That's the currently, well, that's already a bit older. That was a few months ago, our at that time integrated system in our vacuum chamber. I see a few people, a few team members here, Jesse Tarnas, we see Patrick McGarry, Aaron Joe, we got also Lauren Sagan now, David Shea, and Garrett Schieber. And what I'm trying to emphasize here is, again, that illustration, what we're doing, we work in Scrum cycles of 8 weeks where we're integrating all the subsystems together and testing this all the time in a vacuum chamber to make sure that there's no surprises in each of the subsystems. But what's really important is that the requirements that are being fed into the system are driven by a commercial system that I've shown you before, which is, right now a design and a calculation, but the requirements for oxygen generation, for solar cell efficiency, these values are all derived based on our calculations that show what will be required to be able to be more cost effective, for example, than any power system brought from the Earth. And so ultimately, these requirements are really tough to meet. And there's something very unusual for myself as well, coming from the NASA world, where I usually try to make the easiest requirements I can to figure something out. Here, we're driven by very tough requirements that are hard to meet. But so far, we've been actually meeting them beyond expectations, which is, of course, wonderful. And I think, evidence of the amazing team we have here. And what's really important about the Blue Alchemist system, and that's why the name is, Blue Alchemist, we're trying to create an enabler. an enabler that does a lot in one. Because what we're generating here with this core technology is, of course, oxygen for propellants and for human consumption. We're creating power systems, solar power systems for primary production and distribution with our wires. But we're also getting building materials. We're getting glass, we're getting construction materials, we're getting aluminum and iron that we can use for enhancement of other structures. We're really trying to get a system that very effectively uses almost everything we put in to make useful things with it. And therefore, the alchemy part, almost like magic, but it's creating very valuable things out of things that are not valuable. The other thing that's really important for our requirements of driving system is we want to have long lifetimes. So, of course, the demonstration generally has to survive only a few days or maybe even hours, but we're driven again by a commercial system, which would have to operate based on our requirements for at least a few years. Therefore, our requirements for material compatibility and for actually enduring these harsh conditions of high temperature, of high oxidation, are very, very, very strict. Another thing that we're really imposing on ourselves is that we want to be applicable no matter where we go into the solar system, and as easy and as simple as possible, which means that we actually don't want to use any chemicals. We don't want to use any water. And also, because not we don't want to, but as we know, there's not much carbon usually in the moon, so we don't use any carbon. Now, of course, early stages, it's nice and good to work with chemicals and additional process, but we think that ultimately, if we want to have a technology that's going to be allowing us to explore the whole solar system, we have to be independent of this. We can't rely on these things. It's just too complicated. And that ultimately leads to low maintenance because we really have to utilize our robotic exploration experience. We got quite a lot of ex-JPLers in our team that do this pretty well because we don't want to rely on human interaction. So these requirements are really hard, very hard to meet, but so far we're meeting them and we're on track, actually faster than we anticipated, to get this terrestrial demonstration by the next 2.5 years. And some of the subsystems, especially for oxygen generation, will be even matured much earlier, as early as this year, to be infusible into lunar applications. Okay, so I've spoken a little bit now about Blue Alchemist, core technology that's helping us to utilize, or as my dear colleague Emilia says, let's say use, not utilization, using directly regolith to make solar power systems and oxygen. And we're really focused on the moon. But there's another planet that we stand on that's really important. It's our home. It's a home, and it's a home that has a lot of where we've created a lot of issues, and we need to fix a lot of things. Now, the exciting thing is that the technology we're developing currently for space, with applications right now on the moon, the lunar technologies we see, or as we call them, our blue moon technologies, they are driven by low input metalloid extraction from regolith. So that means we're not really having very highly processed ores. We're not getting a big iron clump or a silicon clump and processing this. We're just getting very small concentrations, and we're trying to get them out. We are utilizing technologies that don't use any chemicals, have no toxins, no water, and it's very low input of anything additional but the feedstock we need to build things for solar cell manufacturing. Also, one thing we know already pretty well how to do is make autonomous systems, specifically for solar array assembly. And we've got quite good progress in beneficiation mining technologies. These are the lunar things that we're doing pretty well. And think about this. The nice thing about making space technology and the connection to the Earth is in space, we learn to operate under horrible conditions. That means we learn to make simple systems that need little human maintenance, can live long, survive a lot, and that don't rely on water, liquids, and don't rely on carbon. Now, that leads to implications on this planet and technologies that, per definition, are generally energy efficient, that are actually very green because they don't utilize any carbon, so they have no carbon emissions, no CO2 emissions. And also, we don't use really any chemicals. And a lot of the processing, a lot of industry we do on this planet is very chemistry heavy and very toxic for humans working with this and for the environment. And because we're not affecting anything, don't use water, we also don't affect the water, groundwater levels. And that's, of course, really important because clean groundwater is getting also scarce on this planet. So the terrestrial applications that we see here, and we presented this for the first time now at COP28, the UN Climate Conference in Dubai, last December. We see implications specifically for green steel and green circularity of metals and metalloids, for carbon neutral and clean mining operations, for example, for mine tailings. And we also see ultimately that's the lower hanging fruits, but we also see down the line environmentally sustainable solar cell and solar panel production to really help enable and give power back to the people in remote areas and all over the world. The people are not connected to the grid, or where it's simply not energetically feasible to have a grid nearby. And down the line, as well, infusing these technologies in space-based solar power. And that's, of course, something that, is always been around in the realm of space resource and RSU, is to utilize photons around the Earth wisely for the benefit of this planet. And those things are really important for circularity, not just recycling, but full circularity in utilizing whatever we need in technologies wisely. Of course, climate change mitigation. This is the first time we see here that NASA co-funded technology and space technology is not just helping, again, mitigating climate change passively by monitoring greenhouse gases, but actually actively creating technologies that will help offset carbon emissions on this planet in this decade. It's also going to help us increase supply chain independence. Especially with COVID, we've learned how important and fragile our supply chain is. And it's very important to empower us locally here in the US, but also other countries, of course, to be independent and be able to utilize the resources locally. And it's bringing, again, clean energy into rural and remote areas. So this is the connection where we see how space technology, our blue moon technology, can help create green solutions, green earth technologies. And that's a part where here in Space Systems Development and Blue Origin, in the Space Resources Program, we're really dedicated. And the people that we have on our team are dreamers that want to enable in our decade humans to walk on the moon and explore the solar system. But in the same time, they're very conscious and people who want to help our planet, who want to not just look and explore the beauty, but give back. And this is a way how we as Blue Origin can give back to the Earth, give back to these communities here in the US and all over the world, because many of the problems we have to tackle globally in order to solve them. Okay, now, good timing. We're going to have another sip of water. Because remember in the beginning, I said that there's two things in the solar system. One has to be able to learn where it is and how to utilize in order to really feel comfortable in the solar system. One thing is regolith, the dry stuff. And the other thing, of course, is water. And on the water side, we are very interested in Blue Origin and we're exploring. I won't be able to share very much right now yet, but look out in this year. We're really asking the questions: how can we support our partner NASA and other entities, commercial and national, in order to solve one of the biggest questions of planetary science today, and that is how much hydrogen is there on the moon, specifically in the polar region, specifically in the South Polar region. Where is it? In which form? And is really important to first understand these questions before we can design the technologies to harness it. Depending on the form, the technologies might be very different. And it's so important to us here at Blue Origin because we understand that if we want to have propellants down the line, of course, we've got the oxygen, but we still need, something to, reducing agent, and hydrogen's pretty good at that. So we need to access that hydrogen, but we need to really understand in which form it is. And if we're successful and we can, as a community, answer that question, then we're really going to have a paradigm shift on the moon, a paradigm shift that with the oxygen and the hydrogen and with solar power in between fusing those, it will be a state change. Suddenly imagine we're going to have propellants, we're going to have power. Suddenly the moon, the whole cislunar economy can take a new level. The moon can become, and ultimately cislunar space will become the springboard to explore the solar system. So with that much ado, I kind of want to highlight that we're still not there with tea Earl Grey hot. I wish it would happen in my lifetime. I'm a bit skeptical about that. That was sarcasm. It's hard when you can't see people's faces. So, but I hope you heard that. But what I do think we can do in our lifetime, actually, even in this decade, is understand that the technologies that allow us to take regolith and make power, solar power specifically, make propellants, make metals, and do this in a green, no carbon emission, no water, no chemicals way, that this is really feasible. We're not just talking about it, we're doing it, we're building it. We're putting our money where our mouth is, and that's really important. By demonstrating these technologies, the confidence is being grown and shown that it's not just a dream, it's not far out. IRCU and these technologies are only as far out as our imagination and our understanding of what's really feasible is lacking. If we really see what we're doing in a lab, we understand this is feasible today. And that's why we want to make that change. And with hydrogen, understanding hydrogen, and that's what we're doing as well now, we'll be able to complete this journey. We'll be able to add the hydrogen part and complete the propellants. So please be aware and watch out, because this is going to be a very, very exciting decade, a decade where we're going to be able to change how humanity sees the moon, how humanity sees space resources. It's going to be a decade where space resources will influence climate change mitigation and a more responsible approach towards our planet. I see a great potential in this, and I'd like to close out with a video that's been shared recently by our wonderful comms team. And it's illustrating and showing only a few people in our team. There's many more. And those people are telling a story of what we're doing and telling a story of why we're doing it. Because it's always important not to remember, it's not just what, but why we do things. And I hope you can hear this.
The thing that we're doing in the Space Resources Program is really learning how to live off the land in space without bringing everything from the Earth. And we've managed to actually create a system that's going to do that.
We know from the Apollo missions that the composition of the regolith, the powdery material that blankets the whole surface of the moon, is composed primarily of silicates.
And we will take in that lunar regolith, separate out all of the constituent materials, and create solar panels and oxygen. If we have oxygen and power on the moon, we open up tons of possibilities.
And if we're going to land a power grid on the south pole of the moon, we want to land that in a location that also has the right concentrations of water so that we can extract that resource and turn it into propellants as well. Because once you do that, you can land and take off from the moon at much lower cost compared to what you can do now.
Our goal is to develop space technologies to go to the moon and establish settlements there. But that technology, although it's being developed for space, we can bring that back to the Earth and we can employ it in mining and manufacturing industries and clean up all the emissions, all the wastewater, all the nasty chemicals and toxic fumes in the cities.
We are just at the beginning. We want to learn on the moon, use it as a springboard to test technologies, to learn how to live off the land. The moon will prepare us and help humanity explore the solar system, not just to go there, but to live there.
There you go, folks. And except for me having a really bad hair day then, I hope this was informative. I hope you are excited as much as I am and my team is. And I really encourage you to have as many questions as you have now, or email me later. Again, I might respond later because it's just, we're really, really busy. We got a lot to do. And I want, again, just to highlight that this work is only a result because of an amazing team, amazing people in the lab, in the programmatics, even all over around Blue Origin. Without all that teamwork, this would have never been possible. So thank you, Team Blue. Thank you, Space Resources team. And thank you all for listening to me.
Great talk, Vlada. Thank you very, very much. Really cool stuff. If you have time, we'll jump into the Q&A. I do have a couple in queued up.
Yeah, let's do that. Shall I
so-
stop sharing now?
If you would like, yeah, if you want to leave it up, that's fine too. I'll leave it to you.
Okay.
So first question, has Blue Origin Space Resources Program touched the topic of helium-3 or volatiles in general?
Well, I just spoke a little bit about water, hydrogen. So hydrogen is definitely our first to go to. We're really trying to be very incremental and really think about the first step. So from that perspective, that's why we chose regolith. And from the volatile side, absolutely hydrogen is on our radar.
Awesome. Thank you.
No pun intended.
Next question is, Lunar Cargo PC wants to start something with simpler, more generic, and more impactful. The use of resources for their mechanical properties. And use flat terrain to perform friction landings. Has Blue Origin touched on the topic of geotechnics as a resource?
Yes. I mean, again, there's one thing that we really try to focus, and I want to highlight that there's a lot of things that need to be done, right, in relation to space resource and how we use them. At Blue Origin, our first dedication is to land, and that's what I'm saying. That's really the enable to lift off and land. So our first dedication foremost is to get our landers to the moon and continue doing that and repeat that. And from the space resources side, we're really focusing right now very strongly on the power production, because that's ultimately the biggest needle mover. And of course, oxygen production with that, because without that, nothing's going to happen. We have been working and are still working with partners where we're looking at geotechnics and looking at construction materials. And so we have a lot of exchange there, and we find this very exciting. And so we're happy to learn more about that and exchange with interested partners on that front. But on the landing side, we're definitely looking into that, because we have to know how and where we land and how we can lift off again.
No, absolutely. Well said. The next question is actually three that are around the composition, your work sensitivity to regolith composition. So, hi Vlada, Levi here from Calgary. Great presentation and interesting work. I love the big dream. I have three related questions. One, how much flexibility will Blue Alchemist be able to handle in the compositional variability of feedstock material? We'll start with that one.
Now, this is an excellent question. And again, that's when I was talking about requirements, right? We're very system engineering heavy here, which is important. It's a painful experience to go from the beginning, but we think that if our requirements are not enabling us really to build a very versatile commercial system, then we're not doing a good job. So right now we are focusing very much on our system being capable to intake various iron to magnesium ratios, various iron contents, to be able to also have different mineralogy. And I want to highlight that part. Many times in compositions, right, when we just only work with oxides or try to simulate oxides, it's not the same thing as taking the real minerals. And that's the part where we're really trying to make a big difference by working with real mineralogy, because there are just different binding energies that need to be overcome in different time sequences. So if you don't do this from beginning on, results might be very different. So that's one thing we're changing. So we're working with real minerals that we hope, of course, represent real lunar regolith. And I think that's, the questions to be asked there. What does real regolith chemically, mineralogically really look like? We of course have some good evidence from a lot of samples, but there's still questions that will be open. So in summary, our system is very versatile to handle various mineralogies and chemical compositions, and it's intended and designed to be able to do that. Back to you, Jared.
Cool. Then the next question is, how much regolith compositional mapping is required for these technologies, these areas you work in?
Well, so luckily, I mean, mapping now, maybe if that can be more clearly defined, mapping on where we're landing and what we utilize, or?
I would, Levi, if you have an answer for Vlada's follow-up question, punch it in, but I would assume it means stuff like how much mapping of mineralogy, for example, from remote sensing, do you require to be able to efficiently do what you're doing?
So because of my answer one, not much. That's the idea.
Okay, perfect. Then are there elements or minerals that are best to avoid for this system?
No, not currently.
Cool. Awesome. I think that got to the end that's in the Q&A, but I did personally have a question that I don't know if you'll be able to answer at all. And if not, that's fine. What are you making your molten regolith electrolysis electrodes out of? What's your coating on that? You don't have to answer if you can't.
Yeah, I can't answer this, but I'm going to say this. It's a really good question. And remember, I've highlighted that our requirements that are driving us is longevity. And so all I can say is it's, composition, of course, important, but it's also geometry. There's a lot of aspects that go into making a long-lived system. And all I can say is it's definitely a very, very important thing to consider. And I think we found a elegant solution to pave us through this.
Cool. Well, I hope to hear about it someday at least.
Definitely. And I'll say as well, like I really think it will be lovely. I feel very strongly, and I know it's in my team as well. We love, to have more open dialogue with everybody, and that will come more and more. It just takes always time, because what we do at Blue Origin is we really want to have first really good certainty. We really don't speak out until we have very strong confidence in something and it's been tested and verified and we feel really strongly about it. And even then, we wait until it's very mature, because we don't want to just, give little snippets. We'd rather surprise the world with something that they didn't expect than give them always, small expectations, and, going that way.
Yeah, absolutely. Personally, I think that's a great policy, and it does definitely surprise and wow people. Um, Another question we have is, could you comment on the possible use of Blue Alchemist or related technology for terrestrial mine tailings? There are millions of tailings accumulations around the world of various size, accessibility, environmental impact, and residual resource concentrations. And these tailings represent huge potential for resource extraction and environmental remediation. Any comments?
Yes, absolutely. I can't comment too much right now. I hope I'll be able to do that in the next 2 months or so. Absolutely, yes, that is a very, very good point that's been mentioned, and we're very aware of that.
Cool. I don't see any other questions in the Q&A. I'll give a few quick notices while people think of any last minute questions. Everybody, this will be posted on YouTube shortly, so you'll be able to view it on the AIAA Space Resources YouTube channel. Once I get around to uploading it, sometimes a few things come up and I don't get to it day of, but look for it in the next couple of days. And again, I just wanted to thank you, Vlada, and your team as well for all the awesome work you're doing, and for being willing to share as much as you possibly can on it. You gave a great talk, really interesting stuff, and I look forward to seeing what's next for you guys.
Thank you very much. So I gotta have to check quickly with our comms about that part, Jared, for the posting.
Okay, no problem.
Let you know. But yeah, and I really would love to just encourage everybody to look for all the job recs that we have out, and we'll have even more out. And I just want to really encourage everybody, if possible, two things. One thing is really to not be afraid of things that look too visionary. Sometimes we push this too far into the future. We think, oh, it's step 2.0. But what I like about this technology and what we're doing is sometimes you got to go a little bit further than the bare minimum in order to stay there. So I do really think that RSAU technologies and what we're doing is not just an add-on. It's not something nice to have. It's a must-have if we really don't want to fall back to where we fell back in the last century and decade. This is required in order to not be just a ball that we fall into space and it always falls back to ground. So it's not a nice to have. This is a must have. This is the difference. And I want to really encourage you all to see that it's not just something that it's far out there and difficult. It's very challenging to do it. But when humans come together to face a problem that needs to be solved, they solve it. And it opens up new solutions, as mentioned, for potentially mine tailing remediation and for climate change mitigation. There's a lot of beauty. And I think ultimately space and us developing technologies to stay in space will result in a gift back to the Earth. And that's the ultimate gift that we can give to the Earth, and a gift that's going to allow us to, again, feed back into a space exploration, explain to a lot of communities, maybe challenge why are we doing space, and understand that there's more to it. And I think, looking back at your screen and, Jared right there with ice, there's a lot of things we got to solve on this planet, and this technology will help, not just a little bit, but likely significantly. So I encourage you all to be daring, to realize it's needed, to focus on it, and to validate it, to make it, to do it. Because when you have something in your hands that's working, that's the proof. And then suddenly, all those naysayers, all those who, that's a step 2.0, all that, for those who think it's just, a dream, they shut up immediately and they move on into the new century. So thank you.
Well said. I don't see any more in the Q&A. Vlada's contact information is up. So everybody, thank you for joining us. Vlada, again, thank you for your time and lending your expertise and thoughts here. And with that, we will see you guys next month for the next webinar. Be on the lookout for an announcement shortly.
Thank you very much. Have a
Bye,
good day,
everyone.
Bye.